So this is looking at graphing an inverse trig function. And the key thing here is to know basically what those inverse trig functions look like. So I'm just going into the textbook for a second, and you can see we've got our inverse sine, which has, it's basically just the part of the sine function which makes it a one-to-one function, flipped over the y equals x line. So it's basically a mirror image that will go up and then down. So that's the inverse sine graph. Inverse cosine graph is again just selecting a part of the cosine graph that makes it one-to-one, drawing an imaginary line through which is y equals x, and then flipping the graph. So you can see here the yellow is where you started, the blue is the flipped graph. So this here is our inverse cosine graph, okay? And the last one, inverse tan, this is the funny looking one, because when you flip this over a line y equals x, you see the blue is what you start with, the yellow is where you finish, and what you end up with is instead of vertical asymptotes, you end up with horizontal asymptotes. So the key thing really is to understand what the graphs need to look like, and in the case of inverse tan, where the asymptotes are, and also a little bit about their ranges and domains. Now the ranges and domains are given to you in your formula sheet, and the graph that we're looking at in this example is inverse sine. So it's going to have this kind of basic shape. It may just be flipped. If it's negative, it's going to be flipped the other way, so it would be going that way, and it'll be translated possibly up and down or left and right. So if we have a look at the question, you can see here that there's a dilation factor out the front, and there's also going to be a translation, and that translation will be that way, a half. Okay, so the dilation is really going to affect the range of the function. This dilation is going to affect the domain of the function. Okay, and again, I just tend to draw a little picture. You can see this is positive, so the shape won't change, so it will be going that way, just like our regular inverse sine. Now, this table is out of your formula sheet, and the key thing about this is that this applies to sine x of anything. I'm just going to call this A. Okay, so the domain for inverse sine of anything, any junk, or here anything, it doesn't matter what it is, A can be anything. The domain and the range are as follows. Okay, so what I'm going to do here, this question asks you to sketch the graph and clearly state the implied domain and range. So what I'll do is the domain and range first. Okay, so the domain. Now, what we know is the domain has to be between -1 and 1 of whatever is inside the inverse sine. And see, this really doesn't affect our domain at all. This is what's inside the inverse sine. So that's the thing that goes in between. Okay, so now when we're saying implied domain, this is the domain for the function, -1 to 1. Implied refers to the x and to the y of the function, because that's what we're interested in. That's what our function actually has here. So the implied domain is what values of x can we have, not just what values can this whole inverse sine thing be. So that's where we'd actually solve this equation. Take the half away from every part here, so take a half from here, take a half from here, and take a half from here. So we end up with -3/2 is less than or equal to x, which is less than or equal to a half. So therefore our domain, or what you could call your implied domain for x, is that x has to be in between -3 on 2 and a half. Oops, and square brackets, because it's inclusive. Okay, so that's for our domain. For the range, we have a similar bit of work. So the key thing with the range is, again, sine of whatever is in the brackets the range has to be in between these values. So that means that we've got inverse sine of x plus a half is going to give you output a value that's between, pi on 2 and -pi on 2. That's what this will give you, inverse sine of anything. What we have, unfortunately, is a 2 out the front, but that's cool. All we have to do is multiply everything by 2 here. So we end up with -pi multiplied by pi on 2 by 2 is less than or equal to 2 inverse sine x plus a half. Doesn't matter what's inside there, and that's less than or equal to pi. So that means that for our function, and this is our function here, now our function, and this is y, is in between -pi and pi. So that's the implied range of the function. Now the cool thing with this is is that if you had, any other bits on here, like a +1 or a take away 2 or something, all you'd have to do is take away 2 from each side as well. So the key thing here is to end up with the x and the y, because that's what this implied part is referring to. So our implied range is for y between -pi and pi. So that's the first part done. The next part we need to do is the sketching. So there's a few things you need to know here. Really the intercepts and also any endpoints and the general shape, to be honest. We kind of already know the general shape because we drew ourselves a quick sketch up here. So you really try and memorize the general shapes for those graphs. So the first thing we'll do is we'll try and find the, let's say the x-intercept. So x-intercept is when y equals 0. So all we're going to do is just throw 0 in where y is, to inverse sine x plus a half. We're going to try and solve this now. So all I'm going to do is just pick that up. Let's put that on the next page. And we'll work with that. So we've now got divide both sides by 2. And that just is still 0. Inverse sine x plus a half. And then we take the sine over to the other side, so it becomes sine of 0 equals x plus a half. And this is where you might think, well, sine of what gives you 0? Well, sine is 0 here and here. So you could have 0, you could have pi, you could have negative pi, -2 pi, 2 pi equals x plus a half. Okay, they're your sort of options there. Now, what we have to do is really think about, in terms of the options, okay, where we are with our domain. X has to be between -3/2 and a half. So if we have a look here, these values here are all going to be too big or too small, because we're going to, for x, we have x equals, let's take away a half from everything here. So this is going to be -1/2, this will be pi take away a half, this will be negative pi take away a half. That's obviously too big, and that would be 2 pi take away a half. So if we think about what we want these values to be in between, we want the values to be in between -3/2 and a half. That's not really very much play there, it's in between a half and -1.5. And the only one there that's going to work, that's slightly too big, because that would be a bit over a half. So this is really the only one, and this is a bit too small. So this is the only one that's going to work. So our x-intercept is x equals -1/2. So that's one thing. Let's also find our y-intercept. So x equals 0. And all we're going to do here is simply put that into our function. So we know that our function was y equals 2 inverse sine of x plus a half. But instead of x, we're going to have 0 there. So we put 0 in. Now what we need to do is think 2 inverse sine of a half. We have to think sine of what angle gives us a half. And remember, sine is the opposite. So it's going to be pi on 6. So we've got 2 times pi on 6, which equals pi on 3. So our y-int, oops, is going to be at y equals, let's get rid of that. Our y-intercept is going to be at y equals pi on 3. And we've got our general shape. Remember that our general shape is this kind of look. Okay, we've got our intercepts. Now in terms of endpoints, and we're nearly done, once you actually know what your domain and range is, these are the endpoints of your function. This is the x starting and endpoints, and this is the y starting and endpoints. So we've got -3/2, and -pi is going to be one of the endpoints. So -3/2 and -pi. And the other one is going to be a half, because that was the other half of the domain, and pi. So we've now got everything we need. We can graph this thing. So I'm just going to put some axes down, label them. So we've got y and x. In terms of where you want to label them, we know we have to go up to pi. So it probably makes sense, and we've got a pi on 3 going on here, so it probably makes sense to do this in thirds. So there's pi, and there's pi on 3. I'm not going to have enough room. Just move this up. Just going to move this. That's good actually, because then when you start drawing it, you can sort of see, oh, that's not going to be enough room. So move that up a bit. Start again. So we'll put our axis back again. This is symmetric because you know you've got negative pi to pi. So we'll go 1, 2, 3, 1, 2, 3. So that's pi on 3 there. That's pi. That's negative pi. And we know we have to go to negative 1.5. So I'll go along in halves. So there's a half. There's negative 3 on 2. And I'll go along in halves this way as well. There's a half there. So I know that in terms of the values, there's x, there's y, and the kind of shape that I've got, that's going to work now. So I'm going to just do the graph in red. Key thing, the endpoints, negative 3 over 2 and negative pi, which is here. A half and pi, which is here. The general shape, remember, is this kind of shape. So I'm going to have to fit that in, but also put in my y-intercept, which is pi on 3, and my x-intercept, which is negative a half. So it's kind of join the dots of that kind of, oops, that's a bit dodgy. Let's do that again. That kind of vibe. There we go. So what you want to try and do, and I'm just going to third time's the charm. It's a bit hard with the pen, but that's the kind of look that you want for your graph. Okay, so you've got the same kind of shape that you should have. You should also show your endpoints on here, so actually label them a half and pi. Make sure you've labelled, I've labelled on here what these tick marks are, so that's labelled. And also down here, I'm just going to label that again. Because I've actually showed it on the axes here and here, it is equivalent, but I like to actually put the coordinates at the endpoints just to show that I know what I'm doing. And that's it. So being able to graph one of these inverse functions really requires you to look at a few things. First of all, your implied domain and range, get x and get y. Okay, that's what the implied domain is. And then looking at, once you've done that, being able to find your intercepts, your endpoints, and then identify what shape you need to actually finalize your graph of your inverse function.